Hello everyone. Now I will tell you about my recent work that is called Combinatorial version of the Slepian Wolf coding theorem for binary strings. So we, in this work, we study communication complexity. So here our participants, let's call them Alice, Bob, and Charlie. Here they are. You can memorize their smiley faces. So here's the problem statement. Assume that Alice has some binary string x, a string of n bits, and Bob is given a binary string y of the same length. And both the strings differ from each other in c positions, in c bits, where c is some function of n. And Charlie wants to know both the strings x and y. And to deal with this, Alice and Bob can send bits to Charlie. So they have some channels and can transmit the information. Moreover, all the participants know the parameters n and c. And unfortunately, no communication is possible between Alice and Bob, and no feedback can be sent from Charlie to Alice and Bob. So here is the picture. So as you can see, no communication is available between Alice and Bob, and they send some bits to Charlie. Let's say that Alice sends Charlie some message of length RA, and Bob sends Charlie some message of length RB, and Charlie reconstructs the initial strings x and y from this pair of bits. So the question is, for which pairs such a protocol exists? A protocol, I mean that Charlie will be able to reconstruct the initial pair of strings. It's a combinatorial version of the famous Slepian Wolf theorem. Here the preparation of its formulation, let's say that xy, that pairs x1, y1, and so on to xn and yn be identically independent distributed pairs of random variables where each x, e, and ye range over some finite sets a and b, respectively, and Alice holds some string x, and Bob holds some string y of the same length, and a pair of two real numbers, rx and ry, is called achievable if there exist functions, the following three functions. There are some function that code the initial words to some string of length n times rx, and the same an analog of this coding function. Here it is. And Charlie had some decode function that reconstructs both the initial strings, and we want in this protocol that probability that Charlie decodes some string that he gains some pair that does not matches the initial pair is going to 0 as soon as n goes to infinity. So here's the Slepian Wolf coding theorem. A pair of real numbers rx and ry is achievable if the following three inequalities is holed. Here h is entropy. Well, you just can memorize these three inequalities and look at this picture. So here's the gray area. Is the area where all the achievable pairs are laying at. In my work, I'm studying the two main cases. First, when the distance between x and y is some epsilon constant, and the second case when the distance between them is some constant fraction of n. And let's move to the first case. Here, the lower bound for the pairs RA and RB. For every communication protocol, for our problems, these three inequalities should be satisfied. And the idea of the proof is just standard counting argument. It's really easy. And once again, here's the picture of the admissible region. So everything under these three lines is called admissible region. Here they are all the pairs. And the upper bound here we should give we should give some protocol that solves our problem for some pairs RA and RB. And the theorem states that for every C, there exists a constant D that depends only on C, such that our communication problem can be solved for all pairs satisfying these three inequalities. They are just a little bit differ from the upper bound, from the lower bound, sorry. And you'll see in the picture how it is look like. And moreover, this communication protocol is effective. That is mean that it's deterministic and polynomial in time for all the three participants. So here,
the only difference is D in the first line.
Yeah.
In the equality.
Yes. So here the green lines is where we have our protocol. So the gap between the lower bound and the upper bound is just a constant. So this, I mean that everything that is upper than the green line is also achievable. It's always if we can achieve some optimal state, we can achieve non-optimal states. Here the kind of introduction to how this protocol works. We denote by H some parity check matrix of BCH code, and Alice sends the first L bits from her string X, and Bob, he transmits from the K, from the L plus 1 to the K minus L bits from his string Y. So here we denote by, here we represent strings X and Y as some code words, and that's why code words for the BCH code. And from the information bits, Alice sends as blue squares, and Bob transmits the blue square from his word. And also, except for these information bits, they send syndromes for their words respectively. And it turns out that the total number of transmitted bits is like this, and all the computations is done in polynomial time. But what's the protocol for Charlie? He receives, as you can remember, some bits from Alice and Bob, and after that, it states that he can restore the irrepartent mean X XOR Y from the syndromes, and after that he reconstructs from the partial information bit that was transmitted. He reconstructs X and Y from this information. They are only one of the most involved questions here: how to restore E. Well, here's the idea. Unfortunately, I have a lack of time, so I won't stay here for long. So here's the idea. We restores the irrepartent from just syndromes from these words and guess the irrepartent. So after that, it's very it's not very hard to reconstruct the code words if we have information parts. Okay, so as we learned in the first case, our upper bound, the gap between our upper bound and our lower bound is just a constant. And the second case, when c is some fraction of n, everything is a little bit harder. So here's the lower bounds. It's the same idea of the proof. Here's the admissible region. But in the construct of the first case, not all the points satisfy these bounds can be achieved by some protocol. It was proved by Arlitsky. For example, these 2 points cannot be achieved by some protocol, some deterministic protocol, I mean. So we try probabilistic protocols, and in probabilistic protocols means that Charlie may reconstruct the initial strings with probability with error probability epsilon that is less than a half. And once again, we got the same admissible region, and our main work was in the upper bound for probabilistic protocols. We construct a probabilistic protocol that solves that satisfies all the points, and the gap is only small o of n. Here we use all protocol from except instead of BCH codes, we use least decodable codes, and because of this, we gained lists, and to understand which pair we should take, we use random hashing. Here, center-part modernization and receiving part modernization. So it states that probability is less than epsilon if we use the same construction, but with just different parameters. But unfortunately, there are disadvantages of this protocol that participants need to perform exponentially long computations. And so that's all. Here's a history of the problem. In 1973, the Slepian-Wolf theorem was proved. Then in 2005, a protocol for any arbitrary constant C. That is the first case. And for the second case, we have reached these lower and upper bounds in 2013. So here's our open questions. Can we generalize our results? That means that can we prove that not all the points are achievable by some deterministic protocol? And we wonder if there exists some effective randomized, maybe randomized polynomial protocol for the second case. So here's that's all. Yeah, thank you.
So is there a chance to prove some combinatorial statement from which both probabilistic Slepian-Wolf theorem and your result can be derived? So is there any formal connection between this combinatorial probability and probabilistic version?
Oh, well, the protocol I told you about in the first case can be applied to in Slepian-Wolf coding theorem to achieve some points in that region.
Yeah,
that's the answer.
No general statement which will imply both your result and Slepian-Wolf.
Well, I'm not sure, but I hope so.
So this theorem campaign was slow amount and upper bound.
Sorry?
No, I mean the lower, the constructed part, something which is possible. Upper bound to the last.
Lower. Well, the graphs are the same, so I hope so. Yeah, but I don't know yet.
Also, there is a unique version of this. So
Yes, I know.
So do you have some like real life application? In which case such protocols are needed?
Yeah, well, as I heard,
like to synchronize some databases.
yes, maybe, but I.
We're interested just like in
It's a hot topic, network coding, and there are even a special institute of network coding in Hong Kong, but it's not clear whether they are really getting money or giving money.
Yeah.
What about other fractions? So why are you studying only constant fraction and linear fraction?
Because it's all the possible cases.
Oh, just because clear that for other.
So no, if you have two strings, they can differ in some constant position or in some constant fraction position. That depends on n, on the length of.
Just different kind of asymptotics.
Yes.
There is one trick to get one wave of one asymptotic and another trick of getting another asymptotic. And there are these cases, but C can be arbitrary actually. It's not necessarily a constant.
So linear coefficients. If not, let's think linear ones.